Hello viewers, welcome to this series of lectures on the course CH303, that is Physical Chemistry Part 3 for the third year students of BSc. Today we will be starting with a new unit, that is Unit 3, which is titled as Photochemistry. The session is planned as follows, that is, to begin with we will see what do we mean by photochemistry. Thereafter we will try to differentiate between photochemical and thermochemical or thermal reactions. Thereafter we will talk something about the laws of photochemistry, which are very crucial to understand photochemistry and they are very pertinent in the context of photochemistry. Thereafter we will move on to seeing that what do we understand by absorption of radiation and how do we kind of relate absorption of radiation with the concentration of reactant and things like that. In this context we will learn about what is called as Lambert's law and the Beer's law, because they are two very important laws which we need to understand. And then having done all that, we will try to sum up what we do today in today's session. Now let us make a beginning by defining what do we understand by photochemistry. Photochemistry basically is a branch of chemistry that deals with the study of chemical reactions which proceed in the presence of light. That means, as the name suggests, photochemistry. Photo means light. That means chemistry as a consequence of light. That is a one kind of a general or common way of putting it, that is a chemistry as a consequence of light. That is one way of doing it. But it also includes the reactions that are accompanied by emission of chemical energy as radiation. That means you have a reaction taking place, the energy changes in that they are actually coming out in the terms of a radiation. We will talk more about it as we proceed. So it basically concerns two things, primarily the first one wherein a reaction is taking place because of the light, that is the prime thing here, and also the light is coming out as a consequence of a chemical reaction. Okay. Let us take some examples here. There are plenty of them. The most common one which we come across is the photosynthesis in plants, wherein we know that the carbon dioxide and water they undergo photosynthesis in the presence of light, the sunlight, and give us molecule of glucose. That is a very the most common source of energy for the living creatures around. Let us take another example, say of vision. The chemistry of vision is well understood, and in this whole process photochemistry has a very significant role, which probably at some other time we will be talking about. Another example could be which is again very pertinent, that is the formation of ozone from oxygen in the atmosphere, because that is a very crucial, very important photochemical reaction which is of relevance to anybody and everybody on this planet. Another example could be, which is of interest to everybody, that is bioluminescence in firefly. We have seen a firefly that gives out radiation, that is a example of a luminescence or bioluminescence, because it is a biological system. Thereafter another example could be photography. There again photochemical reactions play a significant role there. Another example could be phototropism, that is orientation of plants towards the direction of sunlight. Again a very important photochemical process of photochemistry is involved in that. Then treatment of jaundice of the newborn babies. There we must have seen that suppose a newborn baby is there and is suffering from jaundice, we put it into some kind of a device wherein we show some light on that. Kind of photochemical reactions take place in that, and that takes care of the problem of the child. Another example could be, which is again that is why we say that light is very important for us, because that leads to biosynthesis of vitamin D in our body. Another example could be photochromism. We use sunglasses because they change color depending on the intensity of light over there. There again is a photochemistry is involved. Or another could be photopolymerization, because lot of polymers is an age of polymers now, and there are a lot of polymerization which are done with the help of light, photopolymerization, and there are many polymers which undergo degradation because of photons and all. So you can see that photochemistry is an area which is very broad, and it touches various aspects of our life, day to day life. Okay. With this brief introduction to the domain of photochemistry, let us move further and try to, as I mentioned earlier, differentiate between two kinds of reactions. They are called as photochemical versus thermal reactions, because typically the kind of reactions we talk about, generally we take something, put into that, put it on a burner, heat it up there, and we are used to reactions which are done by thermal methods. They are called thermochemical reactions or thermal reactions. Whereas in the domain of photochemistry, what we are doing is we are doing photochemical reactions. That means a reaction which is going as a consequence of photon or the light. The reaction will not take place in the absence of light. Okay. So, let us try to differentiate between two the two types of reactions there. Now, to make a case for it, we all know that any chemical reactions to occur, it needs certain amount of energy. And what happens is, for the reaction to occur, we all know from our basic chemistry, that is, the reacting species need to acquire sufficient energy equal to, say, the activation energy to get converted into the products. And then the question comes is, where does this energy come from? One possibility is typically what we have been doing all these times, the thermal reactions. This energy requirement is met by providing some kind of an heat over there. Second possibility is, what happens in case of photochemical reactions is that energy is provided as light or radiation, by which the reactants acquire energy and then go on to the products. So, that is a defining part of it, that is photochemical reactions and thermal reactions. Okay. Now, continuing on this, let us see what happens when a thermal activation takes place. That means, you have a reactants there, you give some heat to that. So, what will happen is, as a consequence of that, the number of collisions between the molecules of the reactant or between the reactant and the walls of container will increase. That is, all of us know that fairly well. That is a typical consequence of a thermal or heat input into the system. Now, what happens to this energy? What happens to the energy is, this thermal energy which has been given to the system, that gets distributed amongst the different types of motion of the molecule, because molecules are undergoing translation, rotation, vibration, and so on and so forth. So, most of the energy gets into the translation, they start moving faster or they start rotating faster, they undergo vibrational excitation, and a small part of that energy gets into the electronic excitations. So, that is what happens in case of thermal reaction. On the contrary, in case of photoactivation, that means, suppose I am providing the energy to the molecule in terms of photon or light, that radiation primarily gets into electronic excitation of the molecules, followed by the reaction. So, that is the basic premise of differentiation over there. That is, in case of photoactivation, energy is going primarily into electronic excitation as against what happens in case of thermal reactions. Yet another point of differentiation is that the thermal reactions typically are accompanied by decrease in free energy, that is, they are spontaneous reactions. That means, a spontaneous reaction can be brought up by thermal means. On the other hand, in the context of photoexcitation, certain reactions which need some kind of free energy increase, or that means, they are accompanied by increase in free energy, or they are non-spontaneous reaction, they also can occur because of the photoexcitation. So, we see the differentiation again. Thermal reactions, delta G has to be negative. For photoexcitation, you can have delta G positive, also positive over there. Now, yet another point of differentiation, the rate of thermal reactions depends on temperature. If you increase the temperature, the rate increases. We all know that fairly well. That is, typically for any chemical reaction, 10 degree increase in temperature roughly doubles the rate of reaction. So, that is all of us are familiar with. But as against these thermal reactions, in case of photochemical reactions, the rate normally is independent of temperature, but it depends on the intensity of radiation. So, in this case, it is not the temperature which is important, it is the intensity of radiation which is important. Now, we will see later on that how does that happen, how does that affect the rate of reaction. Further, the photoexcitation may cause reactions to occur at sufficient speed even at room temperature. That is very, very important again. That is, suppose there is a reaction is there, for that reaction to be performed, we can do it. Suppose the reaction is possible photochemically as well as thermally. So, photochemically that reaction probably can be done at room temperature, because the temperature is not going to matter there. We can increase the intensity of given appropriate kind of radiation, reaction can take place. On the other hand, if I have to perform the same reaction thermally, then probably I have to increase temperature sufficiently large, because if the activation energy happens to be large. So, again the operative temperature becomes important between the two kinds of reactions there. Thermochemical reactions we can done at room temperature, where thermal reactions probably will need different kind of temperature requirements. This is some kind of a illustration here which tells you about the difference between the two kinds of reaction we are talking about. Now, suppose this is a reactant here. In case of thermal reaction, I give some energy, the reactant molecule gets excited, comes to transition state, that gives down to the product side. That is a typical kind of a reactions we are familiar with. On the other hand, in the presence of light, that is, if you are doing a reaction photochemically, what happens is this reactant gets excited electronically, and then thereafter it can get into a electronic excited state, a transition state over there, then you can give it a product there, this product can further get into different kind of products. So, it is just a kind of an overview which tells you pictorially how the two kind of reactions are different there. We will not spend more time on this, probably we will come down to this kind of things little later, maybe in a about a session or two later. Okay. Now, I am sure that by now we know what do we understand of photochemistry and what is the significance of photochemistry, and then thereafter we have been able to differentiate between photochemical and thermochemical reactions in wide variety of ways. Okay. Having done that, let us move further and see that we mentioned initially that the laws of photochemistry are very important. Let us touch upon what are these laws of photochemistry. Broadly speaking, there are two laws which are fundamental. The first one happens to be Grotthuss-Draper's law, and the second one is Stark-Einstein's law. They are very crucial laws. Today it may appear to be trivial, but at the point of time they were given, they were really very relevant. Let us take this one by one. Grotthuss-Draper's law, basically it was stated by Grotthuss in 1817, followed by Draper in 1843. The statement goes as follows, that is, only those radiations that are absorbed by the reacting system can be effective in producing chemical change. Now, this it looks very trivial. Now, suppose the reaction has to take place, unless radiation is absorbed, reaction will not take place. It is but obvious, but that is it was not obvious at that point of time and it was suggested there. The implication is that suppose I have some system there, I am giving some light on that, the light when it falls on the system, it may get reflected or it may get transmitted or get absorbed. So, that portion which gets absorbed, that only causes the reaction, and the one which gets reflected away or gets transmitted through the system will not produce any chemical change. So, that is the significance of this particular simple looking law that is called as a Grotthuss-Draper's law. Okay. Let us move on to the second law called as Stark-Einstein's law. This law was proposed by Stark and Einstein somewhere from 1908 to 1912 and also called as law of photochemical equivalence. It is very important law. What it states is that each atom of the molecule absorbs a single quantum of light. We know that a single quantum of light is called as photon in the process of getting excited. That means, what we have is, suppose there is a molecule M, it will pick up a photon and get excited to become M star or M excited, and in this process it will take up only a single photon. That is the Stark's law or Einstein's law of photochemical equivalence. However, what we find is that in certain cases, typically when we are using very intense lasers as the source of radiation, it has been found that in some cases even two photons have been absorbed, but they are exceptions, not the rule. This is a very important thing. Let us move further. I would like to bring home one very pertinent point about this law is that this law concerns the primary step of activation. What it means is, you have a molecule, radiation is coming, this molecule get excited. For this particular step, this law holds true. It does not really concern or bother about what happens to a molecule thereafter. And what are the possibilities? The possibilities could be that this molecule which has got activated, it may undergo a chain mechanism whereby a large number of molecules can undergo reaction. That means, a lot of product is formed just as a consequence of a single photon absorption. Other possibility could be that this molecule which has got activated does not undergo any reaction, but just gets deactivated. So, what we see from here is that this law of equivalence does not mean that one molecule will react per photon absorbed. The number of molecules which are reacting can be much larger than the number of photons absorbed or much lower than that. So, this is what is referred to as some kind of a quantum yield, which we will be talking about in a later session there, but this is very pertinent here. Now, let us move further and let us see what do we mean by absorption of radiation, because we know that a photochemical reaction is a consequence of absorption of radiation. So, let us understand what do you mean by absorption of radiation, how do we talk about it. Absorption of radiation, you will recall from your earlier exposure to spectroscopy, that is, suppose there are different energy levels, say this is electronic ground state, this is excited state, and a transition has to take place from this level, ground level to excited state, and this is governed by simple Bohr's frequency rule, which says that the frequency of radiation required for this excitation to take place will be E2 minus E1 by h, and that means this E2 and E1 happen to be the energies of the final and the initial state, and h is the Planck's constant. This is very trivial, all of us know fairly well. But how do we express this? Typically in the context of photochemistry, this energy absorbed, that is IA, is generally expressed in terms of a quantity called as Einstein. Einstein is actually the quantity of absorbed radiation there. What does it mean? Let us have a brief look at it. Basically, 1 Einstein of energy corresponds to the amount of energy of 1 mole of photons of a given frequency absorbed by a system. What it means is, now suppose there is 1 photon, say 500 nanometer photon. So, you can work out E is equal to h nu or h c by lambda, you can work out what is the energy of 1 photon. That is too small a number. But if I take 1 mole of photons and put them all together, the energy of all of them, that energy is referred to as 1 Einstein. Let us see it mathematically. Mathematically, 1 Einstein will be equal to, say, Na is the Avogadro's constant and number into h nu, h is the Planck's constant, nu is the frequency of radiation, or we can say Na h c by lambda, where lambda is the wavelength of the radiation there. So, we just substitute the expressions, the values for Na, h and c, we find that, and after a little simplification, we find that the expression can be given as simple as this, that it is 119,666 by lambda, where lambda is the wavelength in nanometers. So, because that we have taken right here as nanometers there. So, once we do this, so this gives you some kind of a conversion factor. That means, just by knowing the wavelength of a photon, we can work out what is the Einstein of that particular thing. That means, if there are 1 mole of those photons, how much of energy will be absorbed. So, that is what we are referring to. Let us say look at the energy equivalents of photons at different wavelengths. We see that 200 nanometers will be about 598.3 kilojoule, and 250, 300, we can keep doing the same calculation. We find that important thing is that higher the wavelength, lower the energy, which is obvious. Okay. So, but only thing is we are talking about in terms of Einstein. That is the point I want to bring home, that Einstein is the energy of 1 mole of photons of any given wavelength. Okay. So, that is what we understand by the kind of units we use for energy absorbed or radiation absorbed. Now, let us say suppose I take a monochromatic radiation and make of intensity I naught, and I make it fall on some sample taken in a suitable container, something like this. You have a cuvette wherein a certain sample is there of, say, concentration C, and some radiation I am trying to light on, I am trying to shine on this having intensity I naught. What can happen is part of that is getting absorbed by the system and rest is coming out as a transmitted radiation. You can see that intensity was large here, it has become faded out here. So, that is I is the transmitted radiation intensity, I naught is the intensity of the incident radiation there. Now, I absorbed I A, which I am interested in, will be I naught minus I. Okay. So, now going further, essentially what we need is that this I naught and I are related by Lambert's-Beer's law, because to know I A, I need to know how do I simplify from I naught and I, and for that to be done, I need to have a look at the Lambert-Beer's laws. Let us see what are these two laws. The Lambert's law or the Boger's law basically relates the light absorption and thickness of the absorbing medium. On the other hand, Beer's law relates the light absorption and the concentration absorbing medium. That means, what happens is, suppose I have a sample here in this container. So, when the radiation is falling, how much of radiation is getting absorbed will depend on what is the thickness of the medium, because when the thickness is more material is there, more molecules are there to get absorb this radiation. Similarly, it also depends on the concentration. So, the dependence on thickness is given by Lambert's law, and that on the concentration is given by Beer's law. And these two laws can be combined together to give you what is called as Lambert's-Beer law or Beer-Lambert law. Let us take these one by one. Boger's law or the Lambert's law, it basically goes as follows, that is, the amount of monochromatic light absorbed by a substance is proportional to the intensity of incident radiation. That is obvious. That is, the ratio of intensity of radiation which is transmitted and incident is constant. So, that is the statement of the law, and what we can see is, another way of putting it is that the intensity of the transmitted light decreases exponentially when the thickness of the substance through which the light is passing increases linearly. What it means is the following. Now suppose I have a medium like this, say of unit thickness. Radiation is coming, say of 100 units, and let me assume that this radiation gets decreased by 10% when passing through 1 unit. So if it is 100 here, it will be 90 coming out of this, because 10% has got absorbed by this. Now suppose I make it double the thickness, then what happens? 100 units are coming there. So from 1 unit of thickness, for the second part of it, now the incident radiation has got intensity of 90. Out of 90, 10% of that means 9 will be absorbed. So what will come out of here will be 81, and it won't be 80, it will be 81. That is what happens. Suppose you take the next one, same thing will continue happening like this. So this whole thing, that is, you can visualize that the thickness of medium can be seen as number of small slices there, and what happens is that this is not decreasing linearly. Thickness is increasing linearly, but the intensity which is decreasing exponentially. That is the meaning of this particular statement there. Okay. Now mathematically it is, I am just giving the statement over there, mathematical expression for that, that is log of I naught by I is equal to k by 2.303 into b, where b happens to be the thickness of the medium and k is a constant. You can say this k by 2.303 is k prime b. Now this I naught and I, we know that they are the intensities of the incident light and that of the transmitted light, and b happens to be the thickness, and this k happens to be in a way a constant of proportionality. Now similarly we talk about Beer's law. As I mentioned earlier, Beer's law concerns the dependence of intensity of transmitted light on the concentration of solution. This also has the same kind of a behavior, that is, the intensity of transmitted light decreases exponentially when the concentration of absorbing substance increases linearly. Suppose I have got say 0.1 molar, 10% is absorbed. If it is 0.2 molar, concentration become double. This will be similar to that, say about from 90 to become 81 and so on and so forth. This is exactly parallel to that too, parallel to the Lambert's law. Let us see the mathematical expression for the Beer's law. We can say that it is log to the base 10 of I naught by I to be equal to another constant k by 2.303 into c, because this depends on the concentration there. And essentially we as earlier, that I naught and I represent the intensities and c happens to be the concentration of the material which is taken into the cuvette, and here we have taken the thickness to be 1 unit thickness. So that is the way we look at the Beer's law. Now we know about the Lambert's law, we now know about the Beer's law. Now suppose I combine the two laws, what do I get? What do I get is the following. I can just give the mathematical expression which reads as follows, that log I naught by I to be equal to ABC. It is very simple to remember, but it is very important to understand the meaning of each one of these terms. A is a constant, is called as absorptivity. B, as before, is the thickness of the medium, and C, as before, is the concentration of the absorbing species. So essentially log I naught by I, it depends on B and C, and A happens to be the constant of proportionality there, but it is called as absorptivity. What does it mean? Let us have a look at it further. Now if the concentration of the material I am talking about is expressed in terms of gram per decimeter cube, and the thickness I take it in centimeter, A will have the units of centimeter inverse, gram inverse, decimeter cube, and that is called as my absorptivity. But typically the thickness is always taken into centimeter, because that is the practical way of doing things. So we always will take it in centimeter, but the concentration we have choice. Suppose instead of taking as gram per decimeter cube, I take the concentration to be in terms of mole per decimeter cube, and B we continue to keep it in centimeter. Then what happens? So this absorptivity will now be called as molar absorptivity, and it will be given in terms of a symbol called as epsilon, and this epsilon or the molar absorptivity will have the units of centimeter inverse, mole inverse, decimeter cube. So now the combined expression, the Lambert-Beer law or Beer-Lambert law expression now will become something like this, log I naught by I to be equal to epsilon BC. So that is the expression which will be using it very often when you talk in terms of photochemistry. Let us make it little further simplified. We do it so by defining a term called as absorbance. The term on the left hand side, that is log I naught by I, is called as absorbance and is given a symbol A. When I do that, what happens is my expression becomes, this is the way I define my absorbance, A to be log of I naught by I. So with this, the expression for Beer-Lambert law then will become as follows, that is log of I naught by I, which we defined as absorbance or equal to A, will be equal to ABC or epsilon BC. And ABC when concentration is in gram per decimeter cube, epsilon BC when concentration is in mole per decimeter cube. A is absorptivity and epsilon is the molar absorptivity, and B in both the cases happens to be the thickness of the medium in centimeter. Okay. Now, let us sum up what we have done today. What we have done today is that we started by defining what is photochemistry, and in the process we saw a lot of examples of photochemical reactions or photochemistry in our day-to-day life. Thereafter, we spent some time on differentiating between photochemical and thermal reactions in terms of variety of parameters. Then we moved on to stating the fundamental laws of photochemistry, that is the Grothes-Dreyfus law and Stark-Einstein law, and explained them and kind of highlighted the significance of each one of them. Thereafter, we explained that the absorption of radiation, which is very crucial for any photochemical reaction to take place, in terms of the Bohr's frequency rule, which is again a very trivial thing, but it was very pertinent to talk about. Then we moved on to, we stated and explained two very important practical laws which basically relate the intensity of light falling on the material and the one which is getting transmitted out of it. And the two laws were Boger's or Lambert's law and the Beer's law. And then thereafter we combined the two together and then saw how do we express them mathematically. Now, in the next session what we will be doing is we will see that what is the consequence of the interaction of radiation with the molecule. That means what happens as a consequence of that, then thereafter what happens to the molecule when it gets excited. So, all this we will be